This is the second video that we've made on hypothesis testing. In the first video, we went through some example questions and how the technique works, and if you haven't seen that video, I would recommend going back to that first before watching this one, because in this video, we're going to cover some more concepts that you need to know for this chapter, okay? So for a hypothesis test, you may need to calculate the critical regions. So here's an example question on this, where we're told at a restaurant, the probability of a customer ordering soup as their starter is 25%. In the last month, though, the manager believes less customers ordering soup as their starter than usual. And the manager took a sample of 50 customers from the last month, and for part A, using a 5% level of significance, we need to find the critical region to test the manager's belief, okay? So the critical region is the region of values where we reject the null hypothesis, which is H0, and we accept the alternative hypothesis, which is H1. We went through the null hypothesis and the alternative hypothesis in the last video, so again, I'd recommend going back to that video if you want to get a recap of that, okay? So this is the region of values where this is the case, okay? So for this question, we need to find the first value of A, where the probability that X is less than or equal to A is less than 0.05. This is 0.05 here because we have a 5% level of significance, so the probability needs to be less than this, and it's less than or equal to A because the manager believes the probability has gone down. So we need to look for when X is less than or equal to a certain value. Okay, so to do this question, we're going to set up the hypothesis test like we talked about in the last video. So remember the steps. The first step is you need to define the null and the alternative hypothesis, okay? So in this question, we're going to say P is equal to the probability of a customer ordering soup as their starter, okay? So the null hypothesis, which is H0, this is what we're assuming to be true, and for this question we're going to assume that the probability of a customer ordering soup as their starter is still 25%. So P is equal to 0.25. This is the probability as a decimal. And then the alternative hypothesis, which is H1, this is what we're testing for, okay? And the manager believes that less customers are ordering soup as their starter than usual. So we are testing that the probability has gone down and it's now less than 0.25, okay? So the second step is we need to set up the binomial distribution. So in this question, we're going to say that capital X is equal to a customer ordering soup as their starter, okay? So in this question, X can be modeled using a binomial distribution. So N is the number of trials, and the manager took a sample of 50 customers, so therefore N is equal to 50, and then P is the probability, and we are going to assume that the probability is 0.25. So this is the binomial distribution that we're going to use. Okay, so we need to find the first value of A where the probability that X is less than or equal to A is less than 0.05. We're using 0.05 because we're using a 5% level of significance. Now, we talked about how to find probabilities like these in the binomial distribution video back in year 1 of chapter 6. So go back to that if you need a reminder. There are a few ways that we can find these probabilities. You can use the binomial table that's given to you in the formula booklet. So what you would do is find where n is equal to 50 and p is equal to 0.25, and then find the first value that has a probability that is less than 0.05, and this would be the critical region. That's one way that you can do it, but the way that I do it personally is using the calculator and using the binomial CD mode on the calculator, where n is equal to 50 and p is equal to 0.25, and I sub in values of x and I find the first x value that gives a probability that is less than 0.05. So if you start subbing in x values, so for example, if you sub in 8, so this is going to be the probability that x is less than or equal to 8. If you put this into your calculator to 4 decimal places, this probability is 0.0916. So this is bigger 0.05, so this probability is too high. So if you instead sub in 7, so this is the probability that x is less than or equal to 7, if you put this into your calculator to 4 decimal places, it's 0.04 0.53, and this is less than 0.05. So 7 is the first value of A where this probability is less than 0.05. So this here is the critical region. By the way, you don't need to worry about values less than this. So for example, if you find the probability that x is less than or equal to 6 to 4 decimal places, this is 0.0194. The probabilities keep getting smaller, okay? So we only need to find the first value here. So this is the first value where the probability is less than 0.05. So therefore, the critical region is where x is less than or equal to 7. So where x is less than or equal to 7, this is where the probability is less than 0.05, and this is where we reject the null hypothesis and we accept the alternative hypothesis. Okay, and then we're told that of the 50 customers, 5 ordered the soup as their starter. And for part B, we need to comment on the manager's belief in light of this information, okay? So 5 is the value of x, so x is equal to 5. And if we look at the critical region is where x is less than or equal to 7. So here, 5 is in the critical region because it's less than or equal to 7. So therefore, it's in the critical region, so therefore we're going to reject the null hypothesis and accept the alternative hypothesis. And remember, we need to write a conclusion, as we talked about in the last video. We're going to say that there is sufficient evidence to support the manager's belief because this value is in the critical region. There is sufficient evidence to suggest that the probability of a customer ordering soup as their starter, the probability is no longer 25%. The probability has gone down. Okay, now for a hypothesis test, there are a few definitions that you need to know of, okay? So firstly, you need to know what a test statistic is, and this is the result from the experiment that we are measuring, okay? And this is always whatever capital X is. So in this example here, this is a customer ordering soup as their starter. This is actually what we're measuring, this is actually what we're interested in. Okay, so next up is the critical value, and this is the first value that falls into the critical region, okay? So for our example here, the critical region is where x is less than or equal to 7, so the critical value is 7, because this is the first value that falls into the region. Okay, so the acceptance region is the region where we accept the null hypothesis. Now, another way of saying this is the acceptance region is the opposite of the critical region. Anything that is not in the critical region is in the acceptance region. So for this example here, the critical region is where x is less than or equal to 7. So the acceptance region is where x is bigger than or equal to 8, because all of these values are not in the critical region. Okay, so next up is the p-value, and weirdly this isn't actually mentioned in the Pearson textbook, but it is mentioned on the specification as something that you need to know, and they have asked exam questions on it before as well. The p-value is the probability of the observed value or anything more extreme than it. So in this question here, the observed value is 5, because of the 50 customers, 5 ordered the soup as their starter, okay? So therefore the p-value is the probability that x is equal to 5 or less than it. This is the probability of the observed value, 5, or anything more extreme than it, so it can be less than 5 as well. And if you put this into your calculator, this probability here, to 4 decimal places, this is 0.0070. So this is the p-value. Okay, so the actual significance level is the probability of a value falling within the critical region, okay? So for this question here, the critical region is where x is less than or equal to 7, so the probability that x is less than or equal to 7 is equal to 0.0453. So this is the actual significance level, or as a percentage, this is 4.53%. This is the probability of x being less than or equal to 7, so this is the probability of a value falling within the critical region. Now, something it talks about in the textbook, and this has also been talked about in exam questions as well, is the actual significance level is also the probability we have incorrectly rejected the null hypothesis. Now, I remember when I was doing A-level stats, I didn't understand why this is the case. I just remembered this going into my exams. But if you think about it enough, this does actually make sense, okay? So this 0.0453, this is the probability of a value falling within the critical region. Remember, the critical region is where we reject the null hypothesis and we accept the alternative hypothesis, okay? Now, this 0.0453 is the probability that x is less than or equal to 7, assuming that the null hypothesis is true and that the probability is equal to 0.25. There is a 4.53% chance that x is less than or equal to 7 and that the null hypothesis is actually true, that p is equal to 0.25. So therefore there is a 4.53% chance that we have incorrectly rejected the null hypothesis and that it is actually true, okay? You don't need to understand this explanation, it's not the end of the world. Just going into your exams, remember that this here is true. Okay, so here's another example question where we're told at a nationwide supermarket, 20% of total customers are signed up to the rewards card. A manager believes at his local store, the proportion of customers who are signed up to the rewards card is higher. He takes a random sample of 40 customers. For part A, using a 5% level of significance, we need to find the critical region to test his belief. Okay, so once again, the critical region is the region of values where we reject the null hypothesis and accept the alternative hypothesis. Now, this example is a bit different from the previous one because in the previous example it was believed the probability has gone down. In this example it's believed the probability has gone up, okay? So for this question we need to find the first value of A where the probability that x is bigger than or equal to A is less than 0.05. In the last example, because it was believed the probability has gone down, we were trying to find the probability that x is less than or equal to A. But in this example here, because we believe the probability has gone up, we need to find the probability that x is bigger than or equal to A. Okay, so remember the steps for setting up a hypothesis test. So the first step is we need to define the null and alternative hypotheses. So in this case, we're going to say P is the probability that a customer is signed up to the rewards card. So the null hypothesis, this is what we're assuming to be true, and we're going to assume that 20% of total customers are signed up to the rewards card. So P is equal to 20% or 0.2, and then the alternative hypotheses is, so the manager believes that the proportion of customers who are signed up to the rewards card is higher at his store. So the alternative hypothesis is that P is greater than 0.2. Okay, so these are the two hypotheses. So now the second step is we need to set up the binomial distribution. So in this case we're going to say x is equal to the number of customers signed up to the rewards card. So x can be modelled using a binomial distribution. So n is the number of trials and he takes a random sample of 40 customers. So n is equal to 40, and then p is the probability, and we're going to assume the probability is 0.2. Okay, so we need to find the first value of A where the probability that x is bigger than or equal to A is less than 0.05. Now this example here we have to approach a bit differently to the previous example because this probability here, your ClassWiz calculator cannot find it directly because this inequality sign is the wrong way round. In order for your ClassWiz calculator to find a probability, it needs the inequality sign to be this way round here. So it's the wrong way round, so we need to approach it a bit differently. The way that we're going to approach this, we're going to use the same method as before where we use the binomial CD mode, sub in n as 40 and p as 0.2, but this time we're going to find the first probability that is bigger than 0.95. okay, so if you start subbing in values of x, if you sub in x is equal to 11, so this is going to be the probability that x is less than or equal to 11. Remember the inequality sign is this way round here. If you put this into your calculator to 4 decimal places, this is 0.9125. Now this isn't bigger than 0.95, so we have to go up by one more. So let's find the probability that x is less than or equal to 12 by subbing in x is equal to 12 into our calculator. To 4 decimal places, this is 0.95 and this is bigger than 0.95. Okay, so what we're going to do with this here, okay, let's find the probability that x is bigger than or equal to 12. Okay, so this is in this correct format here, the probability that x is bigger than or equal to a, where a is equal to 12. Now, we talked about in the binomial distribution video that we've already referenced, in order to find this probability here, we need to find 1 minus the probability that x is less than or equal to 11, and we found this here. This is equal to 0.9125. So this here is 1 minus 0.9125, and if you put 1 minus 0.9125 into your calculator, it's equal to 0.0875. Okay, now we need this to be less than 0.05. This is bigger than 0.05, so this probability is too big. So if we find the probability that x is bigger than or equal to 13 instead, so this is going to be 1 minus the probability that x is less than or equal to 12, and we found that this is 0.9568, so this is equal to 1 minus 0.9568, and if you put this here into your calculator, this is 0.0432, and this here is less than 0.05. So this here is the critical region. This here, x being bigger than or equal to 13, is the critical region. So this is how we find the critical region, where we need to find the probability that x is bigger than or equal to a. Okay, so we're told of the 40 customers, 10 are signed up to the rewards card. For part B, we need to comment on the manager's belief in light of this information. So 10 are signed up to the rewards card, so x is equal to 10. The critical region is where x is bigger than or equal to 13. So x is equal to 10 is not in the critical region, so therefore we cannot reject the null hypothesis, so therefore there is no evidence to support the manager's belief in this case, because x is equal to 10 is not in the critical region. Okay, so let's go through the definitions for this particular question. So the critical value is the first value that falls in the critical region. The critical region is where x is bigger than or equal to 13, so the critical value is 13, okay? The acceptance region is anything that is not the critical region. The critical region is where x is bigger than or equal to 13, so the acceptance region is where x is smaller than or equal to 12. The actual significance level is the probability of a value falling in the critical region. The critical region is where x is bigger than or equal to 13, and the probability that x is bigger than or equal to 13 is 0.0432. So this is the actual significance level. And then the p-value is the probability of the observed value, or more extreme. The observed value is where x is equal to 10, so we need to find the probability that x is bigger than or equal to 10. Okay, so this is equal to the probability of 1 minus the probability that x is less than or equal to 9, because this we can put directly into our calculator. If you put this into your calculator to 4 decimal places, it is 0.7318, and if you put this into your calculator, this is 0.2682. So this is the p-value. So in hypothesis testing, you have something called a one-tailed test and a two-tailed test. A one-tailed test is used when the claim is that the probability has either gone up or it has gone down. It specifically says one or the other, where a two-tailed test is used when it is claimed the probability has changed. It doesn't specify in the claim that they think it's gone up or down, it just says that it has changed and it could go in either direction. Okay, so the way that you'll be able to tell the difference between a one-tail and a two-tail test is on the wording of the question. Okay, so for example, let's say that we have a coin and the question says that I want to see if a coin is biased towards heads. This would be a one-tailed test because it is specifying what direction the probability has gone. It's gone towards heads. Alternatively, it could say it's gone towards tails, but it specifically says what direction it's gone. However, the question could be, I want to see if a coin is biased and it doesn't specify the direction. This is a two-tailed test, okay? Let's say, for example, a restaurant manager believes the proportion of customers ordering pasta has gone down. This is a one-tailed test. But if a restaurant manager believes the proportion of customers ordering the pasta has changed, this is a two-tailed test because it is not specified whether it's gone up or down. Let's say a teacher believes the percentage of students taking the bus to school is higher. This is a one-tailed test because the probability is directed towards one direction. But let's say a teacher believes the percentage of students taking the bus to school is different. This is a two-tailed test because it is not specifying what direction the probability has gone. So there are three main differences between a one and a two-tailed test, okay? The first one is to do with the alternative hypothesis. Let's do the example with the coin that we just talked about, okay? Let's say P is the probability the coin lands on heads. Now, if it says in the question that it's biased towards heads, okay, this is a one-tailed test, and our alternative hypothesis would be that P is bigger than 0.5. If it was a two-tailed test and it just said that the coin was biased, the alternative hypothesis would just be that P is not equal to 0.5. We do not specify if it's bigger than 0.5 or smaller than 0.5. It can go in either direction. We just say it's not equal to 0.5, okay? The second difference is to do with the number of critical regions, okay? In a one-tailed test, we have one critical region, as we've already seen in this video. In a two-tailed test, we have two critical regions. One is for if the probability has gone up, and one is for if the probability has gone down. In the last example in this video, we'll go through how to calculate the critical regions for a two-tailed test, okay? And the third difference, and this is the one that most students forget, is the significance level. For a one-tailed test, we've seen this already in this video, the significance level is unchanged. However, for a two-tailed test, the significance level is halved at each critical region. So let's say that the significance level is 5%. When we are testing each critical region, the significance level will only be 2.5% because it is split in either direction between the two critical regions. Okay, so here's an example question where an archer used to hit his intended target 20% of the time. After taking a long break from archery, he believes the probability of him hitting his intended target now has changed. He shoots 60 arrows and hits his intended target 6 times. Using a 5% significance level, we need to test the archer's belief, okay? So remember how to set up a hypothesis test. The first step is we need to define the null and alternative hypothesis. So let's say that P is equal to the probability the archer hits the target, okay? So the null hypothesis, which is H0, this is what we're assuming is true. We're going to assume that it's still the case that he hits his intended target 20% of the time. So P is equal to 0.2. So the alternative hypothesis, we're told he believes the probability of him hitting his intended target now has changed. So this is a two-tailed test because he hasn't specified whether it's got better or worse, it's just that it's changed. So the alternative hypothesis is that P is no longer equal to 0.2. Okay? So remember the second step, we need to set up the binomial distribution. So let's say that capital X is equal to the number of times the archer hits the target. So this can be modelled using a binomial distribution. So N, so we're told he shoots 60 arrows, so therefore N is equal to 60. And the probability, we're going to assume that the probability of him hitting the target is still 0.2. So this is the binomial distribution that we're going to use here. Okay, so we're told he shoots 60 arrows and hits his intended target 6 times. Now, in the questions so far in this video, we've had to calculate the critical regions. For this question here, we don't actually need to calculate the critical regions. This is similar to the questions we covered in the previous video on hypothesis testing, where instead what we can do is calculate the probability he hits his intended target 6 times and compare this to the significance level. It's a bit of a nicer question, there's not as much work to do. Now, with a two-tailed test, something that's important is the probability can either go up or down, and this impacts the probability we need to find using our calculator. Because if we're testing if the probability has gone gone down, we need to find the probability that x is less than or equal to 6. But if we're testing if the probability has gone up, we need to find the probability that x is bigger than or equal to 6. So which one of these probabilities do we need to find? It's kind of obvious a lot of the time when you look at the question. So an archer used to hit his intended target 20% of the time, and this time he shoots 60 arrows and hits his intended target 6 times. So this is clear we're testing if the probability has gone down, and therefore we're going to be finding this probability here. If you do struggle with this though, there's something it talks about in the textbook, and it's mentioned on the specification as well. You can calculate something called the expected outcome by doing n multiplied by p. So for this question, n is 60 and this is multiplied by p, which is 0.2. If you put this into your calculator, this is 12. This is the expected outcome. And if the observed outcome is lower than the expected outcome, we are testing if the probability has gone down. And if the observed outcome is bigger than the expected value, we are testing if the probability has gone up. So here, the expected outcome is 12, the observed outcome is 6, so therefore we're testing if the probability has gone down, and we're going to be finding the probability that x is less than or equal to 6. However, a lot of the time you can kind of just eyeball it from the question. Okay, so the probability that x is less than or equal to 6, if you put this into your calculator, with n being equal to 60, p being equal to 0.2, and x being equal to 6, if you put this into your calculator to 4 decimal places, this is 0.0308. Okay, now we need to compare this to the significance level. Now it's a 5% significance level, but remember this is a two-tailed test. If it was a one-tailed test, we would compare this value to 0.05 because it's a 5% significance level. However, this is a two-tailed test, so we half the significance level for each critical region. So we're going to compare this to 0.025, and 0.0308 compared to 0.0205, this is bigger than 0.025, so therefore we cannot reject the null hypothesis. So therefore, if we write a conclusion, we say there is no evidence to support the archer's belief. Remember to half this significance level. This is a mistake a lot of students make. Okay, so I'm going to upload a video after this one going through a bunch of past exam questions on binomial hypothesis testing. I've just included this question here as well that's adapted from the June 2023 paper because it includes a couple of details that I haven't mentioned in this video yet that I think are quite important. Okay, so for this question, we're told past information shows that 25% of adults in a large population have a particular allergy, and Ryland believes the proportion that has the allergy differs from 25%. He takes a random sample of 50 adults from the population. Ryland carries out a test of the null hypothesis H0, where p is equal to 0.25 using a 5% level of significance. For part A, for 1 mark, we need to write down the alternative hypothesis for Ryland's test. Okay, so Ryland believes that the proportion that has the allergy differs from 25%. So this is a two-tailed test because he doesn't speculate whether it's gone up or down, he just thinks that it differs. Okay, so it's a two-tailed test, so therefore the alternate hypothesis is going to be that p is not equal to 0.25. Okay, and then for part B, we need to find the critical region for this test. You should state the probability associated with each tail, which should be as close to 2.5% as possible. So this part about it being as close to 2.5% as possible, we're going to ignore this for now. We'll come back to this later. Let's start with finding the binomial distribution. So let's say that x is equal to the number of adults who have the allergy. So we're going to say that x can be modelled using a binomial distribution. It takes a random sample of 50 adults from the population, so n is equal to 50, and we're going to assume the null hypothesis that p is equal to 0.25, so the probability is 0.25. So we need to find the critical regions. Remember, for a two-tailed test, there are two critical regions. There is the lower one for testing if the probability has gone down, and there is the upper one for testing if the probability has gone up. Let's start with finding the lower critical region. Okay, so we need to find the first probability that if it was a one-tailed test, we would find the first probability that is less than 0.05. because we have a 5% level of significance, but because this is a two-tailed test, the level of significance is split in half between the two critical regions. So we need to find the first probability that is less than 0.025. Okay, so use the same method as normal. Use the binomial CD mode on your calculator, sub in n is equal to 50 and p is equal to 0.25, and play around with the values of x until you get the first probability that is less than 0.025. So if you do this, you find that the probability that x is less than or equal to 7 is equal to 0.0453 to 4 decimal places. Now this is bigger than 0.025, so let's go one more. So let's find the probability that x is less than or equal to 6, which if you put this into your calculator is 0.0194, and this is less than 0.025. So normally this is the probability that we would use, and this is the critical region that we would use. However, there is one thing really important with this question. They ask about sometimes in exam questions. It says you should say the probability associated with each tail, which should be as close to 2.5% as possible. Again, they ask this sometimes in exam questions. This means the probability should be as close to 2.5%, or as a decimal, 0.025. It should be as close to 0.025 as possible, even if it goes over. It doesn't matter if it's bigger than 0.025, we just need to find the probability that is as close to it as possible. Now, if you look at these two probabilities here, 0.0453 and 0.0194, you will find that this one here is still the one that is closest to 0.025. It's closer to it than this probability here, okay? So we're still going to use this probability, and we're still going to use this critical region, but keep an eye out for this. It could be bigger than the significance level, okay? So we're going to use this critical region here, that x is less than or equal to 6. This is the lower critical region. Okay, so now we need to find the upper critical region in the case the probability has increased. So we need to find probabilities like this here. So the probability that x is bigger than or equal to a certain value. Now remember, your calculator, the class calculator, cannot directly find these. It needs the inequality sign to be the other way round. We talked about how to counter this issue though. So we need to find the first value of a where the probability that x is bigger than or equal to a is less than this probability here, 0.025. Now because your calculator can only find it the other way, what we're going to do, we're going to plug in values of x into our calculator and find the first probability that is bigger than 0.975. okay, so if we do this, if you plug some values into your calculator, you find the probability that x is less than or equal to 18 to 4 decimal places is 0.9713. Now this here is smaller than 0.975, so if we go one more, if we find the probability that x is less than or equal to 19 to 4 decimal places is 0.9861, and this here is bigger than 0.975. okay, so if we consider this, so the probability that x is bigger than or equal to 19, so this is of this format here, the probability that x is bigger than or equal to a. So the way that we figure this out, this is equal to 1 minus the probability that x is less than or equal to 18, and we figured out that this is 1 minus, and then the probability that x is less than or equal to 18 is this here, this 0.9713. okay, and if you put this into your calculator, this is 0.0287. okay, so we have this probability here. Now this is bigger than the 0.025. okay, so now if we consider the probability that x is bigger than or equal to 20, so this is equal to 1 minus the probability that x is less than or equal to 19, so this is 1 minus this 0.9861, and if you put this into your calculator, this is equal to 0.0139, and this is smaller than the 0.025. Okay, so these two probabilities here, 0.0287 is bigger than 0.025 and 0.0139 is smaller than 0.025. So normally we would take this value here, but remember, for the probability associated with each tail, it should be as close to 2.5% as possible. As I talked about before, it can go over this. We just need to find the probability that is closest to it. And if you look at these two values here, 0.0287 and 0.0139, this probability is actually closer to 0.025. So therefore, we're going to use this probability here, even though it's actually bigger than 0.025. So the upper critical region is where x is bigger than or equal to 19. So this is the upper critical region. So therefore, the two critical regions are where x is less than or equal to 6. This is the lower one, or the upper one is where x is bigger than or equal to 19. So these here are the critical regions. Okay, and then for part C, we need to state the actual significance level of the test for 1 mark. So we talked about the actual significance level. This is the probability that a value lies in the critical region. So either x is less than or equal to 6 or x is bigger than or equal to 19. We have the probabilities here. For a two-tailed test where we have two critical regions, we add these two values together. So it's going to be 0.0194 plus 0.0287. If you put this into your calculator, this is 0.0481. So this here is the actual significance level. Okay, so we're told that Ryland finds that 10 of the adults in his sample have the allergy, and for part D we need to state the conclusion of Ryland's hypothesis test for 1 mark. Okay, so Ryland finds that 10 of the adults in his sample have the allergy, so x is equal to 10. So if we consider the critical region here, x has to be less than or equal to 6 or bigger than or equal to 19. X is equal to 10 does not lie in the critical region. So therefore we cannot reject the null hypothesis, and we say there is no evidence to support Ryland's belief as our conclusion.